The next speaker is going to talk about temperate urban climate, field experiment and modeling studies on urban height island to urban albedo. The topic is of great interest in today's context since due to increasing urbanization, studies have shown that many cities are experiencing extreme heat waves more frequently and the urban heat island intensity in many cities has increased drastically because of the imminent effect on climate change. Our speaker is a senior lecturer and director of Centre for Architecture and Sustainable Environment at the University of Kent, UK. It gives me immense pleasure in welcoming Dr. Giridharan Renganathan.
Hello everyone, greetings from United Kingdom. Before I start my talk, I briefly indicate where I'm from. I'm from University of Kent. University of Kent has its main campus in Canterbury. Canterbury is a historical city and it is a beautiful place to visit. University of Kent too has a beautiful campus, and Kent School of Architecture and Planning is located in Marlow building, which is shown over here. Kent School of Architecture and Planning has 3 research centers, and they are known as CREATE, CASE, and DARK. I'm attached to CASE, which is known as Center for Architecture and Sustainable Environment. What you see over here are the members of the research center. I'm the current director. We mainly carry out research on environment and social sustainability related issues. So if anyone wishes to study or establish research collaboration, or visit, please don't hesitate to contact me. I'm happy to help. Now, today I'm going to talk about field experiment and modeling studies on urban heat island to urban albedo in the context of temperate urban climate. Now, computer models should be sensitive to design parameters to improve urban climate in a meaningful way. However, field experiment is essential to validate and calibrate the models in terms of design parameters. In this context, I'm going to talk about 3 projects. The first one is London Urban Heat Island project, which was funded by EPSRC, and this led to the project on London site-specific air temperature model, which eventually became a PhD work. These 2 led to the development of Urban Albedo project. Now, before I moved to UK, I worked in Hong Kong, where I studied urban heat island extensively. That also influenced me in developing the Urban Albedo project. Now, London Urban Heat Island project was funded by EPSRC and it was carried out during 2006-2009 period. UCL was the principal investigator and Brunel was one of the research partners. And I worked for Brunel University as a postdoctoral fellow. However, the base data for this project came from research work done by Richard Watkins during the period to 1999-2000. He measured the outdoor temperature in various locations of London using British Museum as the focal point. He followed a radial path in 8 directions to measure these points, and he used Langley as the reference point, which is shown in green here. For measurement, he used tiny tag loggers, and they were placed inside an aluminium shield, and these aluminium shields were mounted onto lamppost. And he used a special telescopic pole to install the loggers as well as download the data. Now, we repeated the measurement in these locations during 2007 and 2008. However, we didn't measure in all locations. We measured in 8 in 24 locations along the 8 directions. For the study, we classified the location into 3 geographical zones. They are mainly based on distance from the focal point, which is the British Museum, and density of the setting. The geographical classifications are co, urban, and semi-urban. Co had 20 measurement points, urban had 24 measurement points, and semi-urban had 33 measurement points. For the purpose of analysis, we control the data in terms of geography and then disaggregate the data along the sky conditions and analyze the hourly UHI trends. In core area, we found both during day and night there is UHI. However, the nighttime UHI is very prominent. In urban area, the prominency is similar both in day and night. But when you move to semi-urban area, daytime prominency is much more than the night time. Then we studied the changes in the outdoor temperature using on-site variables such as surface albedo, aspect ratio, thermal mass, green density ratio, plant density ratio, and fabric density ratio. For this purpose, we developed regression models controlling the sky conditions. And we developed both daytime and nighttime models. The daytime model shown here was not significant. The R-squared was very low. This is largely due to the absence of on-site solar radiation measurement and wind velocity. However, all 6 variables were in line with all 6 variables were behaving in line with the acceptable premises. Then we modeled the night time. The R-squared values went up, so the models were very significant, and all 6 variables behaved in line with the acceptable premises. This shows the 6 variables were good enough to explain the changes in night time. Then we control the geography and then carried out the analysis. And when here again, we found the nighttime models were very significant and all the variables behaved in line with the acceptable premises, except surface albedo in urban area. This is largely due to lack of variation in surface albedo in urban areas. In urban areas, you'll find mostly asphalt and concrete paving. So that is being reflected in the model. Key findings from this work: UHI problem is more sensitive in urban areas. During partially cloudy periods in urban areas, maximum daytime and nocturnal UHIs were 8 and 7 degrees respectively. This suggests that the anthropogenic heat plays a significant role in London UHI. The most significant on-site variable was surface albedo, and there was a need for localized temperature data beyond this project, which led to the development of London site-specific air temperature models. For London site-specific air temperature models, we used artificial neural network technique. And input parameters were air temperature, relative humidity, wind velocity, cloud cover, and solar radiation intensity. And these were based on E-through weather data. And other input parameter is on-site the fixed air temperature of a specific site. And we used the 2000 data to train these models. Now, advantage of using neural network is it has the capacity to randomly select data from the database and train the model, and then use the balance data for calibration. For this particular model development, we use 70% of the 99 2000 data for training and balance 30 for calibration. So one of the calibration graphs, we calibrated for almost all the sites, and this is one of the locations in the core area. And you can see in 99, the calibration alignment was very good, and even in 2007, you could see very high calibration. We also predicted cooling degree days for 1999 and 2000, and we could see very good alignment. Then we predicted cooling degree days along the radial paths and try to explain that in terms of on-site variables. The key takeaway from this work, the London site-specific air temperature models were capable of predicting hourly temperature. The accuracy increased for daily values. It is a good tool to work out the local heating and cooling degree days. The inaccuracy sets in where urban variations are high, and again, surface albedo was one of those factors. These two projects led to the development of urban albedo. The urban albedo is slightly different from surface albedo. Urban albedo is a function of urban geometry, aspect ratio, surface reflectance, and so on. Originally, this project was developed in 2009 when I was at Brunel, and we submitted to EPSRC. We had good reviews. We went up to the last stage. However, we didn't get the funding. Then I moved to Loughborough. Then I didn't have time to focus on this project. Then when I moved back, when I moved to Kent, I thought of revising and submitting the proposal. Now, when I revised the proposal, I took into account the comments given by the reviewers, because we had two excellent reviews for the first submission, and there was one moderate review. So I took all those comments into account and revised the proposal. Especially, we strengthened the proposal in terms of material characterization by bringing in Bala Vaidyanathan from Loughborough. Now, when I costed the proposal, it came out to 1 million, and I realized that the reviewers will be reluctant to give or award the project to a person who hasn't got that experience, because I didn't handle a project of that nature before. So I want to nominate somebody else as the PI for this project. The natural choice is Maria Colacotrani, because she was the PI at the first stage, since I was not eligible at that time, because EPSRC did not allow postdoctoral people to become PI at that stage. So if I make her as the PI, the bulk of the money will go to Brunel University. So I wanted to get the bulk of the money to Kent University, and we were doing the experimental work as well. So I negotiated with Maria Colacotroni and Bala to make Marilina Nicolapolo as the PI for this project. Finally, everybody agreed, and we made Marilina Nicolapolo as the working PI for this project. And we submitted in 2017, and we were successful. The project has 5 work packages. The first one is survey of urban typologies and albedo measurements. This is under the University of Kent. And the second task is development of experimental model and data generation. This is under University of Kent. Then the third task is weathering test and assessment of optical properties. This is under Loughborough University. And the fourth task is development of urban albedo calculator. This is a joint work, but University of Kent is leading the component. And the last one is urban modeling and simulation, which is under Brunel University. Approach for University of Kent component, we carried out a site survey, and then we developed 1:10 scale model covering a 100-meter radius of UHI measurement point. So we selected the site from the work done by Richard Watkins. Then we kind of validate the experimental model using the survey information. Then we developed a radiance model of the experimental site, and then we calibrated that model. And then we subjected that model to various changes in terms of geometry and material, especially more precisely, I could say we carried out sensitive analysis to see whether the model is sensitive to various changes. And then we were planning to, the next stage is to develop a radiance model for the actual site, and then simulate various results so that we can generate data to develop indexed and validate the calculator. The survey and scanning now. The 3D scanning was carried out for the actual site, and it was carried out using a Faro focus 3D camera. What you see here is the point cloud data of the 3D scanning, and we also surveyed the site using a cherry picker. So we measured albedo at different levels. Then we developed the experimental model in northwestern location of University of Kent. We selected a site which was a sump in the past, but currently it is not in operation. The estates kindly agreed to give us that site, which you see on the right top image. However, we didn't realize that we had to get planning clearance to build a model. So all this process took about 6 months. Then eventually we did the setting out, and then we developed the model. The base structure for the model was made out of plywood. Then we installed the pyranometers. The pyranometer that we use is Huxflux. Then we are using Campbell data logger to log the data. And now if you go to Google Earth, you could see the experimental site that you see over in this image. And we have industrial partners in the project. Ipstock is one of them, and they gave us 5,400 bread bricks, and Mali is another one. They gave about 600 clay roof tiles. Of course, glass we bought with project money. This is the model for Stanley Terrace site. The model is reasonably representative of the context. And this is one of the locations which was measured by Richard Watkins for his UHI work. So we selected a site based on that, and we selected this because the variation in geometry is not complex, and second one is the height is manageable, so that we can construct 1:10 model. The site surrounding was covered with black tarpaulin to avoid solar radiation getting into the site from low angle solar radiations. Then we also developed IR filter to assess the IR component of the radiation. Now, when I say we developed the filter, IR filter sheets were flat ones. So we have to mold the filters so that they can be fit to pyranometers. So we tried various combination and finally we settled for this arrangement. But by the time the first lockdown was introduced, so we couldn't get any data based on this arrangement, but we do have some data on the other options. Then we carried out sensitivity tests. The first one is based on application of concrete paving, then application of facade color. Then we hope to carry sensitivity test based on aluminium cladding and curtain wall. First, we looked at the impact of rainfall on urban albedo, and we could see on rainy days the urban albedo drops by 0.1. It's dropped about 50%. Then we looked at the impact of concrete paving. What you see here is the black one is the dry asphalt, and then the gray one is with paving. And what we could see is that between 50 and 350 watts per meter square, there is a increase of 9.3%, and between 600 and 900 watts per meter square, there's an increase of 9.5%. Overall, the increase is about 9%. Then we looked at the impact of paving and facade color. So the black one is as built, the gray is with paving, and the orange one is facade color, and the red one is paving and facade color. And in the range of 50 to 300 watts per meter square, the increase is around 20%, and between 300 and 600 watts per meter square, increase is around 8%, and between 600 and 950 watts per meter square, increase is around 24%. Overall, we could see about 20% increase. Then we looked at the impact of rainfall on paving and color. When we had only paving, the reduction was about 33%. Only facade color, the reduction was about 20%. And the combined effect, the reduction was about 20%. Then we also looked at the impact of IR filter by looking at the IR albedo. However, we found some noise in the data, especially at the low angle, which you can see here when the radiation is 0 to 50 watts per meter square. We could see the pyranometer, which was capturing the reflected radiation, was taking some direct radiation as well. So as a result, there was some noise. So this has been eliminated now. However, we couldn't do any monitoring because of the lockdown. So in the coming months, we hope to get some data on this. In principle, we could see there's about 50% increase in IR albedo, right? Then we developed the experimental model in radiance. For that, what we did was we scanned the experimental model and then subjected that to radiance analysis, right? First scanned the experimental site and developed a 3D model, and then subjected that to radiance analysis. And then we calibrated that, and on the first column, what you see is the on-site measurement, and the other column shows in terms of number of reflection in the canyon. So as the reflection increases, you could see the error is getting reduced. But after 5 reflections, the reduction is not that significant. So we decided to stick to 5 reflection in our model. This also saves substantial computer modeling time. So what you see over here is the calibration graphs for different sky condition: clear sky, partially, and cloudy. Overall, the error is within plus minus 10%. And we carried out sensitive analysis. The first sensitivity test was on reflectance. We increased the wall reflectance from 0.3 to 0.6, and we found the albedo increase within the range of 28 to 30% depending on the sky condition. Then we replaced the flow on the ground with brick, because originally it's asphalt, so we replaced the asphalt with brick, which with a reflection of 0.3, and we found the albedo increased by 100% for all sky conditions, roughly 100% for all sky conditions. Then we carried out sensitive analysis in terms of pavement and flat roof. Again, we found when we introduced the pavement in radiance model, the albedo goes up, and for flat roof on sunny days it drops, and then subsequently it increases and is in line with the accepted premises. In general, we found in high latitude locations some rays reflected from the slope to get into canyon as well. Okay. Then we carried out sensitive analysis in terms of canyon aspect ratio. First, we increased the height on the right hand side of the street, then we increased the left hand side of the street, then we increased the both sides, and we found the changes in urban albedo in line with the acceptable premises. So what we could see is increasing aspect ratio reduces the gauge canyon albedo. Orientation of the street influence the gauge canyon impact on the changes in albedo. That is, when the orientation changes, the kind of impact that you get from gauge canyon albedo also changes. Then we wanted to kind of enhance calibration. So we carried out sensitive analysis in terms of specularity and location of the pyranometer. Now, initial studies, yeah, the outgoing pyranometer at the eaves level, the incoming at the ground level. And then we found at certain angles, the outgoing has much more radiation than the incoming one. This is because the outgoing one was getting direct radiation as well as reflection from roofs and etc. So as a result, we were getting unreasonable albedo values. So we moved the pyranometers at the eave side level, both pyranometers, incoming as well as outgoing. Then we also changed the specularity level of the material. For example, we changed the red brick specularity to 0.015. Initially, when we carried out the calibration, we had specularity as 0. So when we changed that specularity, we found the alignments were much more good, and then the error also reduced substantially. But we couldn't reduce the error reasonably well in overcast conditions, because representing the overcast condition in radiance is a challenge. So we are still working on that. Next, now we have built the experimental site model in radiance and modeled it. And next, we are going to build the actual site model in radiance. That is, we are going to take the point cloud data of the actual site and build a radiance model and then validate that model against the experimental model, and then we'll carry out changes in that actual model to generate data. And these will be fed into the urban calculator framework. Now we have a calculator framework, but it needs much more refinement, and for that need a lot of measured data. Since the lockout came in, we couldn't get the necessary data and refine the calculator. Hopefully in the coming months we will get that data and refine the calculator. Of course, we had a lot of challenges. First is vandalism. Twice the site was vandalized, and then we rectified and put the site into operation. And there were quite a few times weather-related damage. So we were able to rectify and put the site into operation. And finally, the pandemic. So since last March, we couldn't do any effective experimental work. We hope in the coming months, from March onwards up to July, we'll be able to do some good experimental work, because we have got an extension. Conclusions. Urban Albedo project will endeavor to develop a user-friendly calculator. Urban designers and architects should take up more interest in experimental-based research. It is important to develop context-specific information, data, and tools for day-to-day application. Funding should be available for context-specific research. These are some of the key references related to the project. Finally, I would like to thank the organizers for inviting me for this conference. Thank you very much.
Thank you, Dr. Giridharan Renganathan, for your insightful presentation on urbanization and its impact on urban heat island effect. I am sure that the audience have found it to be a very informative presentation. Now we shall take a short break for a sponsor video, post which we shall proceed to our next speaker.
Ultratech Lightcon is lightweight, smart filler concrete used as a filling and leveling material. Ultratech Lightcon has been awarded Green Pro certification product by Green Products and Service Council. Benefits to end customer. First, no mechanical vibrators are used, so it saves cost. Second, it provides excellent sound insulation, which help create spaces where sound from neighboring rooms do not create disturbance. Third, it is fire resistant. It can reduce damage to structure in case of fire. Fourth, long-lasting roofs of structure as it is lightweight concrete. Fifth, heat insulation, hence can help reduce the electricity bill by keeping the area cooler. Sixth, it can be used as a leveling course without adding dead weight, thus ensuring good working surface. Benefits to the applicator and technical influencer. First, Ultratech Lightcon possesses excellent workability and can be placed in any desired shape, so applicators can use it in various shapes. Second, the process of application is easier, as it is easy to handle and easy to spread. Third, this concrete has better fire resistance, excellent heat and sound insulation, thus giving the applicator talking points to charge premium and be able to technically provide solutions to the needs of his customers, making him seen as an expert. Fourth, it allows easy handling at the time of placement. Fifth, it can be applied with all traditional surface finishes, paint, tiles, carpets, etc., hence easy for the applicator to use the product. Ultratech Lightcon is lightweight, smart filler concrete used as a filling and leveling material, thereby reducing the dead load on structure and provides ease of placement. Let's learn about its application process. It is a concrete with lower density foam concrete or thermocol beads. The concrete is delivered to site using both transit mixers or buckets as per the requirement of the customer. Since Ultratech Lightcon is typically used as a filler material and on roofs, it is advisable that proper planning is made to transport the concrete from delivery point, from the transit mixer to the point of placement. Normally it is done manually. However, in case of larger pore sizes, pumping may be performed. Light corn can be easily spread and leveled with least amount of efforts. Light corn hardens in about 24 to 36 hours so as to allow people to walk over it.